Welcome to another lesson on problem solving. This time we're going to take a closer look at problem solving with units using the conversion line technique. So whenever we're dealing with unit analysis, basically problems that involve units, you always want to identify the units that are involved and the units that you expect for the answer, right? You need to know what units you're starting with and what units you want to finish up with, and that'll help you set up your conversion line. Remember some things like you can't add or subtract numbers with different units. It's like trying to add or subtract apples and oranges. But you can combine different units through multiplication, division, or raising powers, right? So like miles per hour is a division of miles divided by hour. So that's totally fine. So we can multiply and divide with different units. We just can't add and subtract. So when you want to get rid of a division, the easiest thing to do is to just think of it as a reciprocal, and then you're going to multiply by its reciprocal. So remember that when you're dealing with fractions, dividing by a fraction is the same thing as multiplying by its reciprocal, which means just flip it. So instead of dividing by 60 seconds per minute or 60 s's per minute, I'm thinking seconds per minute, which I guess that's the conversion, 60 seconds per minute. You can multiply by 1 minute per every 60 seconds, right? So that's what a reciprocal is. You just flip that fraction. Okay, let's look at an example. You're planning to make pesto and need to buy basil, or basil, as they say in other countries. At the grocery store, you can buy small containers of it priced at $2.99 for each 2/3 of an ounce container. At the farmer's market, you can buy it in bunches for $12 per pound. Which is the better deal? Well, obviously to compare them, we need them both in the same unit of measure. So we can convert the ounces price to pounds price, or we could convert the pounds price to ounces price. I would probably go the other way of doing pounds to ounces, and I wouldn't have to worry about this whole 2/3 things. But since we want to look at it both ways, instead of dividing by 2/3, we could multiply by the conversion of 16 ounces per pound. So there's my cost per ounce times 16 ounces per pound. The ounces will cancel, and I'll be left with $2.99 times 16 divided by 2/3, which you got to remember is the same thing as multiplying by 3/2. And that comes out to $72 per pound. So obviously $12 per pound is a huge savings, but do you need a pound of basil is the other thing you need to ask yourself, because that's also 4 times as much money. So something to think about, right? Obviously it's cheaper per unit of measure, but do you need that much of it? That's kind of the catch-22 of places like Costco, where you can get things a lot cheaper, but then you have to buy a lot more of it, and sometimes it just ends up going to waste. So here's another one. Your destination is 90 miles away. Your fuel gauge shows that your gas tank is 1/4 full. Your tank holds 12 gallons of gas, so therefore if it's 1/4 full, you really only have 3 gallons of gas left, and your car averages about 25 miles per gallon. Do you need to stop for gas? Well, if you've got 3 gallons and you can do 25 miles per gallon, then 3 times 25 tells me I can only do 75 miles, and yep, I better get gas. But if you wanted to be more specific about it, you could take that 90 miles, you could divide it by the miles per gallon that you get, which is really the same thing as just multiplying by 1 gallon over 25 miles so that the miles will cancel, right? That whole conversion line, it's nice because you know, oh, I want the miles on the bottom to cancel out miles. And then you get 90 gallons divided by 25 and you get 3.6 and you go, yep, I'm going to need more than the 3 gallons that I have. Okay, how about units of energy and power? So energy is what makes matter move or heat up. The international metric unit is joule. Power is the rate at which energy is used, and the international metric for that is watts. So 1 watt equals 1 joule per second. So a kilowatt hour is a unit of measure where it's a kilo is 1,000. It's 1,000 watts per hour, or roughly 3.6 million joules. Sounds like a big number because joules are small. So a utility company charges 15 cents per kilowatt hour of electricity. How much does it cost to keep a 100-watt light bulb on for a week? How much will you save in a year if you replace the bulb with an LED bulb that provides the same amount of light for only 25 watts of power? Well, let's see. 100 watts times 1 kilowatt over 1,000 watts, right? The watts cancel, and you get 1 kilowatt times 100 divided by 1,000 times 1 week, where 1 week is 7 days over a week, 24 hours over a day, right? And you basically get 16.8 kilowatt hours, because the only thing that are left are kilowatts and hours. So 1 week, right, a 100-watt bulb for 1 week that's just on constantly for 1 week would cost you 16.8 kilowatt hours. And if they charge 15 cents per kilowatt hours, we just multiply that by 15 cents per kil, right? Those cancel. And you get 252 cents, which is $2.52. So it costs you $2.52 a week to keep that $100 or so that 100-watt light bulb on constantly. Now, since the LED thing, it takes 25 watts, that's 1/4 as much. So you'll only use 1/4 as much energy, which means your weekly cost will be the same thing divided by 4, which is just 63 cents. In other words, you'll be saving $1.89 per week. So in a year, you'll save about $98. Again, that's if a light bulb's on for 24 hours a day, right? 7 days a week. So you have to weigh these things, especially with the cost of an LED light bulb versus the cost of an incandescent, right? So it's all the things you have to take into consideration. Okay, units of density and concentration. Density describes compactness or crowding. So how dense something is how closely together the granules are, right? Whatever it is you're looking at. So material density is given in units of mass per unit volume or grams per cubic centimeter. Population density is given by the number of people per unit area, usually people per square mile or people per square kilometer. And then information density is given in units of mass per unit volume, so like gigabytes per square inch. Concentration, however, describes the amount of one substance mixed with another. So the concentration of an air pollutant is often measured by the number of molecules of that pollutant per 1 million molecules, and it's called ppm, so parts per million. So when they talk about something having 17 ppm, that just means there's 17 basically molecules of that pollutant in every million molecules of air. Blood alcohol content describes the concentration of alcohol in a person's body, where grams of alcohol per 100 milliliters of blood is where blood alcohol content comes from. That's how it's measured. So here's a really important example, because this is something that nurses have to deal with every day. A child weighing 18 kilograms has a bacterial ear infection. The physician orders treatment with amoxicillin, a typical antibiotic in the penicillin family, at a dosage based on 30 milligrams per kilogram of body weight per day, divided into doses every 12 hours. Sounds like a lot, but if you break it down into bits and pieces, it's not too much. So the question is, how much amoxicillin should the children be prescribed every 12 hours? And then if the medicine is to be taken in a liquid form, and that liquid suspension contains 25 milligrams per milliliter, how much should the child take every 12 hours? First thing we got to do is figure out how much they need, right? Well, they're supposed to get 30 milligrams per kilogram of body weight per day, but because it's given in 2 doses every 12 hours, we cut that in half, right? They need 15 milligrams for each dose. So we need 15 milligrams per kilogram of body weight. So a child weighing 15 kilograms would just be 15 milligrams per kilogram times that 15 kilograms, and the kgs would cancel, right? And you'd be left with 15 times 15, or 225 milligrams. So they need 225 milligrams for each dose. So every 12 hours, they need to take 225 milligrams. Well, you call down to the pharmacy and you get, some liquid amoxicillin, and they're not going to give you pure amoxicillin. It comes in a mixture. It comes in a suspension, right? And in that suspension, there's 25 milligrams of amoxicillin per milliliter of the liquid, right? The rest of the liquid is, probably like a saline kind of solution type of thing. So now we need to figure out how much of that actual liquid do we need to give the child every 12 hours. If they need 225 milligrams and there's only 25 milligrams per milliliter of the liquid, basically how many milliliters they need. So again, we use the conversion line. We've got 225 milligrams is what we need, and we need to divide that up by this conversion rate, but it's easier to just always do multiplication where we use that conversion rate of 25 milligrams per 1 milliliter. We just flip the script and put it on the bottom so that the milligrams will cancel. So we can cancel out milligrams and we're left with milliliters on top, and we do 225 divided by 25 and we get 9 milligrams. So every 12 hours you got to give them 9 milliliters of that liquid medicine, because in that 9 milliliters, they will end up getting 225 milligrams of the medicine, with the rest just being the filler, the saline kind of solution. All right, so those are some examples of how to use the conversion line with unit conversion and unit analysis.